Okay, in this video I'm just going to show you all of the solutions to homework 3. And I'll just go through it and show you each sort of screenshot. You can pause it where you need to check your answers. So in problem number 1 we have the first set of problems is some basic loss budgeting. And in problem 1A, to find the minimum transmitted power, I got 7.94 milliwatts, approximately 8 milliwatts, or 9 dBm, using these equations. For part B, I got 22.6 dB for the system margin. And for part C, I got 19 dBm for the transmitted power when the margin was set at 10. For problem 2, it's very similar, almost exactly the same calculations with different numbers. And in part A, I got the minimum transmitted power is 3162 milliwatts, or 35 dBm. For part B, I solved for the margin with this given transmitted power, and I got 0.44 dB. So just barely positive, barely enough to make the system work. For part C, finding the transmission power that yields a margin of 10 dB, I got 45 dBm. And that ought to be about 10 dB more than the transmitted power in part B, because its margin was about 0. And in fact it is. It's about 10 dB more than the 35.44 dB for part B. So that makes sense. Problem 3, we're given a minimum. We're given the receiver sensitivity here is minus 20 dBm. We're given the transmitted power, and we need to find the maximum channel loss. That's easy. Once I convert the transmitted power into dBm, 27 dBm, and I get 47 decibels as the maximum channel loss for part A. For part B, we're going to go ahead and set the channel loss at just 42 decibels. It's 5 dB less, and so we expect to get a margin of 5 dB. Plugging into the equations, indeed, we get 5 dB. For problem 4, we have an RF amplifier with a gain given as 26 decibels, and we have the input power, and we need to find the output power. Well, we can do it two ways, either in decibel units or in linear units. And first I converted my input power into dBm, and then I'll use the decibel approach to find the output power. Minus 16 plus 26 is 10 dBm, or 10 milliwatts. If I go with the ratio approach, I can turn the gain into a ratio. It's a ratio of 400. And now the output power in milliwatts is the product of the gain ratio and the gain and the input power in milliwatts. So it's important that these quantities in this equation are in milliwatts and gain ratio. And notice the difference between, let me add a layer here. Notice the difference between this equation where everything's in dB units and this equation where everything's in linear units. Okay? In any case, you get the same result, 10 milliwatts, either way. For number 5, we're given the loss of the air channel, and we're given 2 gains, and we're also given quite high losses on the cabling, and asked to find the channel loss. Well, the channel loss includes the air channel. Channel loss is decreased when you have positive gains on your antennas, but the channel loss is increased when you have cabling losses. And you plug in, you get 81.2 decibels for the channel loss for problem 5. For problem 6, presumably, here we go. For problem 6, we're given the air loss, we're given the gains, we're given the same cabling losses, and we're asked to calculate the channel loss again. Here the gains are given in dBd units though, and that's something that we need to convert into dBi units in order to combine the gains with the air loss. Okay, so here I'm going to convert these two gain quantities into dBi units by adding 2.15 decibels to the dBd units. And here's sort of the picture I use for this. Here, represented at the far right, is the gain of some antenna. And this gain can be measured either relative to the gain of a dipole or relative to an isotropic antenna. Okay, and it turns out that the isotropic is a reference of 0 dB, and that the dipole antenna has a gain of 2.15 dB. In other words, the gain in dBd units relative to the dipole is 2.15 less than the gain relative to the isotropic. And so we have the equation that the gain in dBd plus 2.15 is the gain isotropic. So we get 7.15 for each, plug into the equation, and we get 58.8 decibels for the channel loss here in this one. Moving on to problem 7. We're going to let the transmitted power be given. We're going to let our receiver sensitivity be given. We're going to ignore cabling losses and find the maximum air channel loss when we have 0 gain antennas. Plugging into the equation yields basically I draw this picture first and then write down the equation and then solve for the quantity I need to get, and I got the maximum air loss as 85 decibels. And then we have various other values for the gain, and you recalculate and you get 89.3 decibels for part B, 133 decibels for part C, and 10 decibels for part D. Okay, and in part D we went ahead and got a new air loss, new loss of the air channel. Okay, so those are values. On any of these, let me know if you disagree with my answers. I may have made a mistake somewhere. In problem 8, we're given transmitted power, gains, cabling loss, very high cabling losses, and air channel loss and receiver sensitivity, and we need to find the margin. So again, I write down the equations. Here we're going to combine the equation which has the channel loss and the margin in it with the equation that puts the channel loss in terms of the air channel loss, the air loss, okay, and the gains and the cabling losses. And you can plug all this together, and on this one I got 16.15 dB for the margin. On problem 9, now we're doing some air channel calculations, and we're going to use the equation for air channel loss in decibel units, 32.4, and here R is in kilometers and F is in megahertz. You can calculate, let's see, we're given the wavelength and the distance and the transmitted power, and we need to find the received power. So we're going to find the air channel loss. And you know what, this doesn't mention anything about antenna gains. To be a realistic problem, we have to have antenna gains because we don't have any purely isotropic antennas. But here we're not given anything, so we're going to go ahead and assume isotropic antennas, calculate our frequency, turn our in the frequency in megahertz, the distance in kilometers, plug into the equations, and we're going to get negative 25.9 dBm as the received power. And I think I'll stop here on this video and move on, starting problem 10 on the next video.